Hello, my name is Daniel Lunsford, and this is my Physics2212Lab5 Faraday's Law lab report. So for the introduction, the purpose was to collect data on a magnet falling through an aluminum tube in order to observe the effects of and apply Faraday's law. Some of the fundamentals we used were Faraday's law, Biot-Savart law, Newton's second and third laws, Ohm's law, the magnetic force in a loop, and the derivative of magnetic flux with respect to time, which are pictured on the right. And then some of the results from the lab experiment were 1.8 seconds for our experimental time and 1.12 for the computational time. Some models and assumptions. Model was the magnet was used to model a magnetic dipole, while the aluminum foil wrap tube was used to show magnetic braking. And some of the assumptions we made were air resistance was negligible, and gravity and the magnetic force from the aluminum were the only forces acting on the magnet. So for the experiment, the system was the aluminum tube and the magnet. Surroundings was everything else. And then for the procedure, we used a magnetometer to identify the north and the south pole of the magnet. Then we dropped the magnet through the tube 5 times and recorded the time it took for the magnet to reach the bottom of the tube. And then here's some of the measurements and data. The trial 1 was 1.84, trial 2 1.76 seconds, trial 3 1.72, trial 4 1.88. And then trial 5 1.8 for an average of 1.8. And for the checkpoint questions, why can't we use a ferrous tube, for example, a steel pipe? And then we can't use a steel pipe because a ferrous tube contains iron, which is magnetic and would affect the velocity of the falling magnet. And what happens to the magnet? How does this compare to a magnet falling in free space without a tube? The magnet falls slowly down the tube due to the magnetic force from the induced current in the aluminum. Then for the glow script model, here is the initialization of the code and some of the constants we used. Then here is the geometry of the tube, the parameters of the simulation, and creating the tube of foil as rings stacked along the y-axis. And then here is creating the bar magnet and some of the constants we used, or the magnitude of mu. And then here is defining the magnetic dipole and the differential, the flux differential. And then the rest of it is showing the actual simulation of the magnet dropping, the gravitational force, and calculating the magnetic force and applying Newton's second law. And then here is the actual model itself, with the red being the north pole, the south being the blue side, and then it falling down the aluminum tube. Then here's the graph from the model. On the left is the graph with a mu value of 4.5, which is accurate to what we saw, and then on the right is mu equals 2.2, which is what we calculated from lab 3, which turned out to give a sort of inaccurate graph. Then for the glow script model questions, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which counterclockwise, and how can you know? Using Lenz's law, the red current corresponds to counterclockwise and the blue clockwise. And then what happens to the dynamics of the system when you flip the magnet around? The magnet would still fall through at roughly the same rate, but the induced current would be flipped. And then how does the total time in tube of your real-world system compare to that of a computational system? And how might the computational system be made more accurate? Both were quite accurate using adjusted mu value, but the computational model could be made more accurate by redoing experiment 3 and trying to come up with a more accurate mu value. And then what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Initially, the force of gravity and the induced magnetic force were uneven, causing the magnet to accelerate, but as time went on, the forces became more equal, slowing the magnet, and toward the end of the tube, the forces once again became uneven, causing the magnet to accelerate out of the tube. And for the discussion, there were likely no model discrepancies. The sources of error were human error and with recording or calculating the mu value from lab 3. And then the discussion questions: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Due to Ohm's law, the induced current and thus the induced magnetic field would be much greater, potentially stopping the magnet from falling entirely. And then what if holes were cut into the tube? How would this affect the ring currents in your model? through holes in the conductive material, it would disrupt the path of the induced current, causing the rings in the current or in the model to decrease. And then for the conclusion, this lab gave us insight into how Faraday's law works in real life and the effects of induced current and induced magnetic fields. And it also gave us a real-world example of how a changing EMF and magnetic flux work, which are important fundamental principles we take for granted. Thank you.